All right, let's dive into one of the most mind-bending, reality-warping concepts in all of modern physics, time crystals. And trust me, this isn't just some cool sci-fi idea. It's a real discovery that's forcing us to rethink the very definition of matter itself. So, let me just throw this at you right away. What if you could have something that is in constant, perpetual motion, forever, but uses absolutely zero energy? I know, it sounds completely impossible, right? Like it shatters the fundamental laws of physics. But as you're about to see, the reality is so much weirder and more interesting than that. So the big question is, what on earth is a time crystal? How can something move eternally, especially when it's in its lowest possible energy state? Well, to figure that out, we actually have to start by taking a step back and rethinking what we thought we knew about a regular old crystal. You see, time crystals aren't just a new material, they are an entirely new phase of matter. But here's the catch. They're not like a solid, a liquid, or a gas, states that exist in a nice, stable equilibrium. Nope, time crystals belong to a whole new category called a non-equilibrium phase. And that, right there, is the secret to all of their bizarre behavior. Now, you really gotta focus on that phrase, lowest energy state. Normally in physics, when something hits its ground state, its absolute minimum energy level, all the interesting motion is supposed to stop. It's like a hot cup of coffee that's cooled down to room temperature. Everything just settles. A time crystal completely ignores that rule. Even at its most chilled out, lowest energy state, its particles are locked into a rhythmic, repeating dance that just keeps on going. To really wrap our heads around how a time crystal can do this, we need to start with something familiar, like a regular diamond or a snowflake. The whole magic trick here is a concept called symmetry breaking. Now, I know that sounds super technical, but it's an idea you actually see all the time. Just think about a glass of water. As a liquid, all those water molecules are just tumbling around randomly. It doesn't matter where you look inside that glass. Up, down, left, right, it's all basically the same. That's a state of high symmetry. But what happens when you freeze it? Boom! The atoms snap into place, forming a rigid, perfectly ordered, repeating pattern, an ice crystal. All of a sudden, that perfect sameness is gone. The system has spontaneously broken its symmetry in space to create that beautiful, ordered structure. So, the key takeaway is simple. A regular crystal has a pattern that repeats over and over again in space. Its atoms are arranged in a predictable grid. Okay, you got that? Good. Now, let's take that exact same idea of symmetry breaking and apply it to a whole new dimension. So if a regular crystal breaks symmetry in space, what do you think a time crystal does? Yep, it does exactly what it says on the tin. It breaks symmetry in time. Now, this is a really big deal. In physics, there's this core principle called time translation symmetry. It's just a fancy way of saying that the laws of the universe don't change. Gravity works the same way yesterday as it does today. It's a fundamental concept, and it's directly tied to the law of conservation of energy. So, if a time crystal breaks this symmetry, isn't it breaking physics itself? Well, here's the incredibly clever way it actually works. The time crystals we've made are called driven time crystals. So imagine you're pushing a kid on a swing. You give a push every, say, 2 seconds. That's your driving force, with a period we'll call t. Normally, the kid swings back and forth with that same period, t. But a time crystal, get this, it does something absolutely wild. Even if you poke it every 2 seconds, it might only respond every 4 seconds or every 6. It just spontaneously decides to adopt its own, slower rhythm, completely breaking the time symmetry you're trying to force on it. And this brings us right back to that perpetual motion question. Is this free energy? And the answer, this is really important, is a firm no. The laws of thermodynamics are safe. As the quote says, energy is still conserved, but you have to look at the overall system, which includes the laser or magnet that's doing the pushing. The time crystal isn't pulling energy out of thin air. It's just found a new, unbelievably stable way to exist when it's being poked from the outside. You know, the journey to actually make one of these things was a total scientific roller coaster. It's just a perfect example of how science works, with big ideas, major setbacks, and then brilliant breakthroughs. The whole story kicks off in 2012, when Nobel Prize winner Frank Wilczek first cooked up the wild idea. But then, just a few years later, in 2015, a no-go theorem came out that seemed to prove it was totally impossible, at least for a system in equilibrium. That could have been the end of the story, but scientists pivoted. They realized, hey, what if it's not in equilibrium? What if we drive it? And by 2017, they were proven right. Two different labs created the first real-deal time crystals. And just this year, 2024, a new one was built that stayed stable for a mind-boggling 40 minutes, proving this is way more than just a weird little flicker. So, okay, this is all incredibly cool, but does it matter for anything outside of a physics lab? Absolutely. Discovering a new phase of matter is like discovering a new continent. It opens up an entirely new map of possibilities we didn't even know existed. What this all boils down to is that time crystals are a brand new frontier. They're a whole class of matter that plays by a different set of rules, forcing us to literally rewrite the textbooks. And their crazy stability is what's getting people really excited. It might offer a solution to one of the gnarliest problems in quantum computing: how to build a stable memory that doesn't just fall apart. Beyond that, it's kicked open the door to whole new areas of physics that we'll be exploring for decades.
So think about it. We've found a way to impose a repeating, crystal-like pattern onto time itself. We've created a state of matter that, just a decade ago, was considered impossible. And that really makes you wonder, what other impossible things are out there, just waiting for us to find them?